year I've had in synthetic biology in those 17 years. That's the cover of The Economist from April, Redesigning Life, the Promise of Synthetic Biology. It's treating this industry like electronics as a broadly applicable technology that's going to hit many markets. I was at the White House on Monday where they hosted a summit on America's bioeconomy. This is in parallel to a summit they held a year and a half ago for artificial intelligence. And what you see is the White House saying, look, there are emerging technology platforms that the US has to be fundamental in. We have to win an industrial base there. One of them is AI. Another one is synthetic biology. That's the kind of league we're playing in now. And so I think this is very much a new thing for the industry. And my shorthand on it is we're sort of maturing, right? You might have noticed earlier, about 9 months ago now, Twist went public. We've been one of Twist's biggest customers since 5 years ago when the company was 30 people, and we did a big deal with them. The company's valued around $1 billion today. We raised a $290 million fundraising round just three or four weeks ago now, valuing the company at $4 billion. The companies in the space are starting to grow up, and I love this photo. So this is from our industry meeting last week out in San Francisco, SynBioBeta, and that's John Cumbers, the founder of our industry group, and he skateboarded onto the stage in that ridiculous parka. And just to explain it, the skateboard has a spider silk polymer in there, and that parka, what makes it waterproof yet lightweight is that it also has spider silk coating made from genetically engineered yeast cells from a company called Spiber in Japan. So these are some of the first really exciting consumer products coming out of these new materials companies. But I think it's also clear that, like, my view is synthetic biology, we're kind of like a teenager, right? We're a little awkward, we're skateboarding, but we're coming into our own and need to take more and more responsibility about building this industry. And so I'm really excited. We have a couple great speakers in this vein today. Marijn Decker's going to be interviewed by David Freeman. Marijn was there when Thermo went from being Thermo Electron and bought Fisher and made the modern Thermo Fisher as CEO during that period, most recently CEO of Bayer, knows what it looks like to mature a new industry. And then a great conversation between Mike, who's the CEO at Kronos Group, and Christina at Ginkgo, about how do we think about the responsibility associated with our technology as we deploy it in new markets. And they're going to speak about responsibility in the cannabis industry, which is one of the most active areas for synthetic biology today. Okay, so that's why I want to give sort of an update, right? I think we're hitting our teenager phase. We're growing up a bit as an industry. Where does Ginkgo fit into that emerging industry? Okay, so I'm going to tell you two pieces of this. One is sort of the nerdy technical bit, which I'm going to start with because I can't help myself. And then the second is all the other things we need to do to support the ecosystem. So the nerdy bit, what Ginkgo's been building, basically, if you remember Tom's analogy, we're programming cells like we program computers. Well, how do you program computers? Right? When an app shows up on your phone, how did it get built? What are the tools needed to build it? Well, what a software engineer uses at an Uber or Google is what's called an integrated development environment, okay? An IDE. And it has three things in it: a code editor, a compiler, and a debugger. And here's how it works. You go in the code editor, which is a little window on your computer screen, and you write human-readable language. If this, for that, at least it's readable by some humans, computer programmers. And then you hit compile, and compiler is a translator. It converts human-readable code into zeros and ones. It's a machine code that can be read by the processor. And then the processor runs, and the debugger pops up, and it's like, this is broken, that's broken, that's broken. You should really go fix it. You go back to the code editor, and you make your changes. You hit compile. Debugger comes up again. It's still broken, and you go around and around that loop thousands of times with a team of developers until you're like, this is good. It's good enough. Let's ship it. And then it goes out to the App Store, and you all get to download it. That's the process by which we make these software apps. That's what we've been building at Ginkgo. We've been building a compiler and debugger, an IDE, for programming cells, okay? And so I'm going to go down one layer here and explain what that looks like for programming a cell. So here it is for a computer, human-readable code to zeros and ones. What's that look like for programming a cell? Oh, that looks like DNA synthesis. Our code is not zeros and ones, it's A, T, C's, and G's. We have to build that code. So companies like Twist, you send them that sequence of letters, and they print that DNA, right? We bought Gen9, one of the other companies in that space 3 years ago. So if you do the tour later, you'll see in Bioworks 3, our compiler, where we build DNA. Okay, and so that's sort of what compiling looks like. And then once you've got that DNA, it's got to go into the genome of the cell. And that's why you see all the robotics at Ginkgo. We're doing molecular biology to insert that DNA into the genome of a cell. Okay? What about debugging? All right? You're going to get this is what a cell programming debugger looks like. Up on the left, I'll share a little piece of history for you from the computer industry. So that's a PDP-6. Okay, it was a time-sharing computer. So this was back in the 60s when computers were so expensive that people had to share them. Okay, you couldn't get one for yourself. And that little document down at the bottom is I'll read it to you. It says a multiple processor DDT. And DDT stands for Deck Debugging Tape. And that's written by one Thomas Knight at the ripe age of 20 and sent out as a memo to the AI department at MIT. This is one of the first real-time debuggers ever written for a computer. Okay, if you want to have real nerd cred, you write one of the first real-time debuggers for a computer when you're 20 at MIT. All right, and so Tom, this is the kind of expertise we have that we're bringing to the problem and saying, what would a debugger look like for programming a cell? All right, and it looks real different. A cell is a physical object. If we want to know what's going on inside, we've got to open that thing up. We've got to look at the proteins, the chemicals, everything that's happening inside the cell. And so that's a little closer. If you take a tour of Bioworks 2 and Bioworks 4, you'll stand inside a 40,000 square foot debugger for cells. All right? And I'm really excited today, and this afternoon you're going to hear from Eric Hobbs. We just announced last week a $150 million order for Eric's technology into Ginkgo. This is, as far as I'm concerned, the most interesting new debugging technology for cells on the market. And I won't take Eric's thunder, but it's sort of like tractor beams for moving cells around. It's kind of like Starship Enterprise over there. And so you'll get to see a couple of those if you do the tour in Bioworks 4. And so Ginkgo makes these investments in Twist, in Berkeley Lights, big orders, because we believe we need to bring this technology together to reduce the cost of compiling and debugging. And that's the key takeaway for what Ginkgo's been building on the technology side. We make big fixed cost investments in our facility, external or building our own robotics and software, to increase the amount of compiling and debugging we can do. And alongside that, the cost falls. It's like an auto plant. It's like a semiconductor fab. It's like an Amazon warehouse. The more of it we do, the cheaper it gets. And then we pass that value on to our customers who have much lower cost to compile and debug code and write new cell apps. Does that make sense? And so we've been roughly tripling our output annually and halving our cost from this scale economic in programming cells for the last 5 years, each year. As you can see, the numbers are up since last year. This is the most important internal metrics at Ginkgo. OK, so that's as much as I want to say on the technology. It requires more than technology to bring a cell out to market, to program a cell and get it on the market. I think of it kind of like a movie studio. If you want to make a movie, the movie studio has technology for you. They have cameras, they have lights, they have a set. But they also have relationships with actors. They have relationships with capital that's interested in funding movies. They have relationships with all the movie distributors or movie theaters that want to show the movie. And you get all that if you're a director that works with them. We have to build all that up, too, for launching cell programs. It's not easy. It's not just the technology. We need the distribution relationships and capital and so on. And so that's a few things we've announced in the last couple of weeks I want to point out in that direction. So we announced a partnership with Petri Bio, which is an incubator right here in Boston, actually in this building on the 6th floor, and Y Combinator out in Silicon Valley. These are incubators that basically fund new companies. You get a few $100,000, you get a couple of new people, start your company, and go launch an app. Well, what about bio companies? So YC's been starting to fund bio companies. It's a lot harder to start a bio company with $200,000. You got to buy lab equipment, all these things, right? We're trying to speed that up closer to software speeds by saying, don't build a lab, just use Ginkgo. We'll program the cell for you, and we'll take some equity in the company in exchange. And so we're rolling that out with the January batches, both for Petri and Y Combinator. The companies will have that opportunity. We're really excited about this. On the talent side, I'm really excited to introduce Jasmina, who you're going to hear from later today. She's built up a brand, Mother Dirt, which is a live cell cosmetic, okay? And she'll tell you more about it. But importantly, she'll be joining us in November as our first entrepreneur in residence at Ginkgo. And so this is talent. This is someone who we want to launch a new cell app and understand what we can do with our platform, bring in some capital, and bring a new cell to market. Okay? And so these are both ways, either in-house or through partners, that we want to recruit great entrepreneurs, like people in this room, who want to launch cell apps on top of Ginkgo. Make sense? All right. And then, well, if the technology is getting faster, the venture capital needs to get faster too. And so there's a whole biotech VC ecosystem that has a certain pace, and there's a technology VC ecosystem that maybe has a little bit of a faster pace. And we want to see those things come closer together. So we have a great panel here. You're going to hear from Susan and Chris and Judy and Sarah and Rachel moderating about what does venture capital look like as this technology matures. Okay, on the capital side, we just announced yesterday Ferment Fund, which is an investment consortium among 3 of our biggest investors at Ginkgo, Viking, Cascade, and General Atlantic. It's a $350 million vehicle, and it's meant to back new spin-outs on top of the platform. So you might remember, about 9 months ago, we announced Motif Foodworks, which you're going to be hearing from the CEO, John, later today. This is a company focused on animal-free meat protein production, okay? And you'll get the details on it. But the structure was, we got great partners, Louis Dreyfus Co., Breakthrough Energy Ventures, Fonterra, who were interested in this market. They invested. And then we also brought financial investors in behind them to launch that spin-out. Well, Ferment Fund makes that possible in a much easier way. Now, if we go to a strategic and they're interested, we can turn around to Ferment Fund and say, let's do this, and fund new spin-outs more easily. And so this is a way for new applications to launch with a lot of capital right out of the gate. And so you're going to hear on these future of food, I think one of the biggest areas for apps in cells coming up, with John and Jeffrey and Catherine and Kristen and David moderating this afternoon. So I'm really excited about this. And hopefully, we launch 2 or 3 more motifs in the next year with Ferment Fund. OK. So that's sort of where Ginkgo fits into the ecosystem, both from a technology and a non-technology standpoint. Why are we so excited about this stuff? And so although computers and cells are similar in the sense that you can program both of them, you can put new code in and make them do new things, they have one big difference, which is computers move information around. So you can tell it to divide this or multiply that or send this information there. You can't tell it to build something. So if you look at what the industries that have been disrupted by computers are, they're information-based. Media, telecom, advertising, finance have all changed completely in the face of computers. Cells are programmable. You can put in new code and make them do something new, but they don't move information around. They move atoms around. Cells build stuff. And so the industries that are going to get disrupted by this technology are physical goods. It's going to be clothing. It's going to be materials. It's going to be medicine, right? It's going to be food. These are the industries that have not been disrupted in the information era, and I think biology is kind of coming for them. They're sort of biotech industries, but they don't realize it yet. Okay? And just to put a point on this, is a slide I like to show. I give a lot of talks in Silicon Valley. And I like to ask, hey, these are some of the most sophisticated devices that we've created as a species. What's the most sophisticated device on the table? And the answer is the houseplant, right? And the answer is obviously the houseplant, right? The houseplant is self-repairing. Imagine if you cracked your iPhone screen and this thing fixed itself over the next 2 days. We'd all be hailing Tim Cook as a god, right? It's self-assembling. You plant a seed and you add air, water, and sunlight, and this thing builds itself with no manufacturing facility. It's self-replicating. You make the first copy, it goes off and makes more copies. What would that do to Apple's margins, right? And then finally, it's renewable. You throw it on the ground, when you're done, it melts away into the environment in a way that totally plays well with the planet. So at a macro level, this is by far the most sophisticated technology. Well, what about at a micro level, right? So you might have looked at like a drop of pond water, in elementary school or something in a microscope and seen these guys swimming around, and I'll draw your attention to that little hair on the end of the bacteria, right? That's what's called a flagella. There's a close-up at the top, right? So you can see a bacteria with these flagellar tails. They're basically propellers. And I'll draw your attention to where the tail meets the body of that microbe. At that junction is this device on the left. It's a flagellar motor. It's a 30,000 RPM rotary motor. Red disc spins inside the blue disc. Okay? To give you a sense of scale, lower right, that's a current generation Intel semiconductor chip. So those two fins, those two silicon fins together make up one transistor. 40 nanometer scale bar. 40 nanometer scale bar on this image of the flagellar motor in the middle. So in the same area where Intel, with a $5 billion manufacturing facility, can make those two dumb hunks of silicon, biology is building a 30,000 RPM rotary motor, placing thousands of atoms in 3 dimensions for free in one of the puddles outside right now, right? And where is that on Intel's roadmap? 100 years out? 500 years out? We have no idea how to do this kind of molecular manufacturing, and biology does it today. So you put these together, and we have nanoscale precision. Biology can place atoms better than Intel, and thanks to self-assembly and self-replication, we have continent-scale production. Think about industrial agriculture. Think about jungles, right? Biology makes more physical stuff every year than the auto industry, the petroleum industry combined. No comparison. So it's better at the small stuff, and it's better at the large stuff. So why don't we use it to make everything? And the answer is, yeah, we are inevitably going to use biology to manufacture everything. Right? All that's missing right now is our ability to program it is poor. And let me tell you, the programming tools are doubling in effectiveness annually. We will catch up. Okay? And so we're going to hear from a couple folks, Aoife on the pharmaceutical side and Mike in agriculture, about how you could push the limits of this technology and where you can apply it in the now. And then also a great panel with Gina and Christoph and Catherine and Natsai about sustainability. This is an area where we have a lot of materials in this room, and many of them are not made in a way that plays well with the planet. How do we deploy engineered cells to make that possible in the future? And then how do we finance that activity? Do you see more demand for that from the capital markets coming up? This will be a really exciting panel to see. OK, so last thing I want to talk about. So we've talked a lot about sort of the kind of practical applications. Could we make renewable plastics or new ways to make foods and things like that? Another thing to keep in mind here as we open up cell programming as a category is it's going to be available to artists and designers to create new things, to make new stories, right? So if you were here last year at Ferment, you all got to smell for the first time a fragrance of an extinct flower, a flower that went extinct in the 1800s in Ohio. A sample was collected. It actually was stored at the Museum of Natural History at Harvard. We took some of that sample, sequenced it, found the part of the DNA that encoded the fragrance, compiled it into a cell, so printed it and put it in the genome of a cell, did some debugging, because it didn't exactly work the first time, did some debugging, and got to a cell that produced those fragrance compounds. And then working with a scent artist, Sissel Tolas, we made a fragrance that captured that lost scent. Okay? And what I'm so excited about, number one, is that in Grow magazine, if you go right in the middle, you can find a little card. It's scratch and sniff, and you can actually smell this yourself today. And then I'm also very excited that this has been touring as part of an art exhibit in partnership with Daisy Ginsburg, an artist that worked on the project with us and Sissel, at a number of places around the world, but is currently at the Cooper Hewitt through January 20th in New York City if you want to go see it. And it's really cool to see people engaging with this. Right? Because I think a big part of what's coming up is how does the public, how does the world at large think about an era where we can program cells like we program computers? Right? What are the stories that we need to tell? How do people need to think about that? Right? And I think we'll learn just as much from the art and design that is developed with this as we will from the practical applications for understanding how, as a society, we adopt this technology. Okay? Towards that end, there's also a great short story in Grow magazine by Andy Gonzalez at Ginkgo and illustrated by Rishi Jain, another employee at Ginkgo, about what happens if we succeed at this stuff. What would that future maybe look like? So I encourage you to read it. It's cool. All right, 2 slides. I just want to end on. So this, I literally just found out about this a couple weeks ago, which I think is amazing. And so, we made Grow magazine because we felt like we wanted people to take home something today that at their leisure they could spend a little more time with and understand SynBio instead of like the fire hose you're going to hear today. And then we found out that IBM actually, back in the 30s, this is the first edition, June 1935, of Think magazine, that IBM used to distribute out to their customers and partners to help them understand what was happening in this emerging data processing and computing industry that no one knew about. And I was like, this is great. I'm like so excited. Although I read, they printed 30,000 copies, and I asked Christina, and we only printed 2,000 copies. So I feel like we got to tweak the ambition. But that is the ambition, right? IBM brought data processing into the world, and that meant building the technology platforms to make it possible. It meant educating people, inventing the term, building the ecosystem around these machines that ended up changing the world. We want to do that with cell programming. We want to build the technology platform. We want to build the ecosystem. We want to collect the talent. And I cannot emphasize enough, it is like day one of this, no question about it. Like we're absolutely just starting. And so if you're in this room, you're going to be a part of that. And we can't wait to see what cells you'll design with us. So welcome to Ferment, and I'm really excited to spend the day with you all. Thanks very much.